Hello everyone, my name is Muhammad Naufal bin Muhammad Nasir, and in this presentation I will summarize a research article titled Molecular Dynamic Study of Grain Boundaries as Defect Sinks Under Irradiation in Lithium Aluminium Oxide and Lithium Penta-Aluminium Octa-Oxide. This study is highly relevant in the field of nuclear materials science, especially for applications such as fusion reactors and tritium production systems. The article investigates the behavior of lithium aluminate ceramics, specifically lithium aluminum oxide and lithium penta-aluminium octa-oxide under irradiation, focusing on the role of grain boundaries in managing radiation-induced defects. These ceramics are widely used in tritium producing burnable absorber rods or TP bars in nuclear reactors. Ensuring these materials can withstand high radiation exposure is critical to reactor safety and efficiency. As we know, radiation in nuclear environments creates defects like vacancies and interstitial atoms. If left unmanaged, these defects can accumulate and degrade the material structure integrity, while prior study have examined single crystal behavior or metallic systems. Few have focused on how grain boundaries interfaces between crystal grains affect dynamics in ceramics. Therefore, this research addressed a key knowledge gap. How do grain boundaries have behaved under radiation in lithium aluminum oxide and lithium penta-aluminium octa-oxide ceramics? And can they serve as effective sinks that absorb and reduce radiation-induced defects? The main objective of these studies are to analyze how defects evolve near grain boundaries under radiation. Compared to simulation models, Buckingham and Reed's FF potential in terms of accuracy and stability determine the behavior of lithium, aluminum, and tritium atoms at around these boundaries. An additional goal is to determine whether lithium penta-aluminium octa-oxide performs better than lithium aluminum oxide under irradiation, which has defects. Implication of material use in nuclear fuel system. This simulation shows displacement cascades at grain boundaries using Buckingham versus ReSFF, and to see how ReSFF avoids void formation. This pictures is the highlights of the structural integrity of lithium aluminum oxide and lithium penta-aluminium octa-oxide, supporting the use of ReSFF in modeling their accurate atomic arrangements. From this image, we validated the crystal structure of lithium aluminum oxide and lithium penta-aluminium octa-oxide using RDF or SRD comparisons, confirming ReSFF accuracy. The authors used molecular dynamics simulations with the LAMMPS software to model displacement cascades near grain boundaries. They created grain structures using the Voronoi tessellation method and introduced a 40 keV lithium atom as a primary knock-on atom to simulate radiation-induced events. Two types of interatomic potentials were tested, which is the first one is the Buckingham potential, which is simpler but less accurate at modeling grain boundary behavior, and more advanced Another one is LIALO2 potential, which includes bond formation and breaking, and it is better at simulating chemical interactions. The simulation results were also validated through a real-world experiment using scanning transmission electron microscopy, stand for STEM, and electron energy loss spectroscopy yields on irradiated lithium aluminum oxide samples. The results shows that grain boundaries act as effective defect sinks in both lithium aluminum oxide and lithium pentaaluminum octoxide interstitial atoms, especially lithium, tend to migrate toward the grain boundaries during displacement cascades. This movement significantly reduces the number of interstitials in the grains and support the hypothesis that grain boundaries help in mitigating radiation damage. Interestingly, lithium pentaaluminum octoxide demonstrated better defect healing capabilities compared to lithium aluminum oxide. This was due to higher atomic mobility and more efficient exchange of lithium and aluminum atoms between the grain interiors and their boundaries. In terms of individual atomic behavior, lithium atoms, being smaller and more mobile, migrated easily to the boundaries, leaving behind vacancies in the grains. Aluminum atoms, on the other hand, were less mobile and tended to remain within the grains as interstitials. This behavior is consistent and experimental observations of lithium pentaaluminum octoxide precipitate formation in the grain centers of irradiated samples. Additionally, the researchers found that the LIALFF potential outperformed the Buckingham potential in nearly every aspect. While the Buckingham model generates unrealistic voids and higher energy readings near grain boundaries, the LIALFF model produced more stable, accurate simulations that match closely with the experimental data. Another important aspect of this study is the behavior of tritium in lithium aluminum oxide. The simulations showed that tritium atoms diffuse quickly through the ceramic and form stable chemical complexes with oxygen atoms such as tritium oxygen bonds, including mono, tri, and tetratritium oxides, which is TO, T3O, and T4O structures were observed. The calculated diffusion coefficients for tritium was 1.33 times 10 power of 14 meters square per second, which is consistent with previous simulation and experimental values. This indicates that lithium aluminum oxide is a reliable method for tritium release, as it allows for effective migration of tritium atoms while maintaining structural integrity. In conclusion, the study provides strong evidence that grain boundaries are crucial and for improving radiation tolerance in lithium aluminate ceramics. Lithium pentaaluminum octoxide shows superior performance in absorbing and healing defects, making it a promising candidate for use in nuclear systems. The LIALFF potential is clearly the more reliable tool for simulating radiation effects in these materials. Finally, the tritium diffusion results confirm that lithium aluminum oxide can be effectively used in TP bar applications, supporting both defect management and tritium transport. That's all from me. Thank you for watching my presentation. I hope this summary was help you understand the significance of grain boundaries in radiation damage, ceramics, and their role in nuclear material performance. If you have any question, I'll be happy to answer them. That's all from me. Thank you.